This is the Earth 2.2 billion years ago. Imagine a world without liquid water, just solid ice in all directions. It would certainly not be a place where most life forms would like to live. Previously, high levels of methane in the atmosphere of this young Earth had generated a greenhouse effect that warmed the planet. Methane is roughly 30 times more potent as a heat-trapping gas than carbon dioxide, which is usually painted as the bad boy of greenhouse gases by media and news. But many scientists think the methane was destroyed by chemical reactions with Earth's first ozone, produced when ultraviolet light from the sun struck the oxygen molecules. They suspect big loss of methane sent Earth crashing into a set of severe and long-lived ice ages, even at low latitudes. So, in this Paleoproterozoic era, the whole planet was covered in ice sheets, even the Earth's largest oceans. This global ice sheet was 1 kilometer thick in average, which is approximately the size of Burj Khalifa, world's tallest building so far. By comparison, Arctic Ocean's sea ice is just few meters thick today. The average temperature on Earth was minus 50 degrees Celsius, plummeted below zero even at the equator. Once it turned into a snowball, it was almost impossible to warm up the planet and restore climate conditions suitable for complex life forms that we have today. But why was it so difficult? Well, fresh snow reflects up to 95% of the incoming sun radiation, and ice reflects 55 to 80% of incoming sunlight, sending that energy back into space before it can warm the planet. By comparison, ocean water reflects just 12%, and land areas reflect between 10 and 40% when not covered with ice and snow, of course. So, the more snow and ice covers the planet, the easier and faster the rest of it will freeze. That's an example of a positive feedback loop. On top of that, sun was 16% fainter than today, which makes it even more difficult to warm up. As most of you know, the oxygen that makes up 21% of the atmosphere is essential for most life forms. However, the atmosphere 2.5 billion years ago contained only 0.001% the present atmospheric levels of free oxygen, rapidly rising 2.2 billion years ago in an event known as the Great Oxygenation. This means that something happened at that point in time, something that thawed the Earth relatively quickly, thus allowing living organisms to flourish and rapidly evolve. But what? What could have turned a planet completely covered with ice into a warm, life-friendly place, full of liquid water? According to some scientists, volcanoes popped through the ice and belched life-saving carbon dioxide. The extra carbon dioxide in the atmosphere caused a super greenhouse effect. But in order to reverse the Snowball Earth, the concentration of carbon dioxide in the atmosphere would need to be several hundred times higher than what our atmosphere contains now. This is a tough challenge for volcanoes, which are more likely to cause cooling by volcanic ash and aerosols than warming by carbon dioxide. If volcanic activity wasn't enough or even counterproductive, then what caused the melting of huge ice sheets? Let's travel to a modern age Western Australia to find the answer. To Yilgarn Craton specifically. It is one of the original masses of rock that rose out of the sea in the late Archean about 2.7 billion years ago to form the original landmass of Australia. At this time, the eastern part of Australia had yet to form. The 65,000 square kilometers of the Yilgarn Craton lies in the southern part of Western Australia. It's resistant to erosion, which makes it suitable for preserving even the oldest geological secrets from Earth's history. Now we will navigate to Barlangi Rock, an ancient hill within this Yilgarn Craton. Scientists took samples of Barlangi Hill rocks, zapped them with 100,000 volts of electricity, breaking them up into their component minerals without damaging delicate textures. Next, they had to sift for crystals suitable for dating, thus picked out several hundred grains of zircon and monazite, each smaller than the width of a human hair. After vaporizing spots on the rims of these crystals with an ion beam, a mass spectrometer measured the abundance of uranium and lead in the vapor contained within the crystal before vaporization. From the proportions and the known half-life of the uranium, an age could be calculated. Scientists ended up with a date of 2.23 billion years old, plus or minus 5 million years. That's the time when these crystals were formed. Why was the dating of crystals and Barlangi Hill significant? Because it was a confirmation of what could have been assumed by simply looking at patterns in mineral crystals and fractures on the Barlangi Hill rocks. It is a clear sign that about 2.23 billion years ago, the Yilgarn crater was struck by an asteroid. The rim of the crater that was left behind, which was called Yarrabubba crater, is not visible to the naked eye though, even from the air, despite its size of nearly 70 kilometers in diameter. This Yarrabubba crater is the oldest Earth's crater, outdating the previously oldest known impact, which was the Rutherford Dome, a 2.02 billion year old feature in South Africa that at 300 kilometers wide is the world's largest. In 2001, a magnetic survey near Yarrabubba revealed the circular features in the bedrock, glimpsing the crater, which was confirmed 2 years later. But the date of it wasn't confirmed until recently, and it almost perfectly matches with the end of the most severe ice age in the Earth's history. The impact came at the tail end of a planet-wide deep freeze known as Snowball Earth. Scientists modeled the effect of a 7-kilometer wide asteroid striking an ice sheet between 2 and 5 kilometers thick. They found the impact could have spread dust thousands of kilometers, darkening ice and enhancing its ability to absorb heat. It also would have sent 500 billion tons of steam into the stratosphere, orders of magnitude more water vapor than in today's stratosphere, where it would have trapped heat. This, probably with a little help of previously mentioned volcanic eruptions, ended the Ice Age. While Yarrabubba impact towing the planet and allowing life to reclaim icy continents and oceans is of huge significance, it won't be the first example of life benefiting from a cosmic blow. Impacts 4 billion years ago could have jump-started life. Asteroids delivered phosphorus, a key nutrient, and the impact also created the protected, energy-rich hydrothermal systems where some biologists believe life began. So, although public tends to associate impacts with extinctions, the geology showed us they sometimes can be bringers of life.